Nobel laureates in physics and chemistry, laureates in economic sciences, members of the Academy, ladies and gentlemen. On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the 2021 Nobel Lectures in Physics and Chemistry and the lecture of the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel. We are just about to enjoy enlightenment from exceptional researchers who will broaden our views in 3 different areas of research. But once again, just like last year, the COVID-19 pandemic means that the format today will deviate from the long Nobel Prize tradition. The Nobel lectures will be delivered from different parts of the world rather than here in Stockholm. It has been a dramatic year with a heartbreaking number of human deaths and immense suffering due to the ravaging COVID-19 coronavirus. But on the other hand, we have seen astounding scientific breakthroughs that have in record time produced vaccines that successfully limit the spread of the virus. When Alfred Nobel wrote his testament in 1895, 1 year before he passed away, he pointed out that the 5 prizes he described should be decided with no consideration of nationality, and the prizes should be awarded to the worthiest person. The last 2 years have indeed made clear to all of us that research is an international endeavor. Regarding the efficiency of vaccines, the numbers speak for themselves. Statistics is an essential tool to analyze large data sets and to understand complex matters. Sadly, however, some people still use anecdotal data to question the efficiency of the vaccines. Such misinformation is propagated unintentionally or even intentionally with devastating consequences in terms of human lives and suffering. Another area where statistics and mathematics are invaluable tools is for understanding complex physical systems like the climate. To realize that climate is changing and why. This has been clarified by this year's Nobel laureates in physics. And here too, opponents have used selected observations in their efforts to disregard the big picture and to disinform. Research is quite obviously a prerequisite for increased understanding and progress. But our societies also need insightful policy decisions to devote sufficient resources to combating pandemics and to achieve sustainable development. This year's laureates in chemistry have discovered and developed novel and ingenious methods to synthesize molecules. Their work allows increased precision and has become useful for a broad range of applications. The economy laureates have introduced and applied new methods in their field. This has allowed correlations to be turned into understanding of causation, leading to important, new and surprising insights. All these achievements not only bring new knowledge and deeper understanding, but already allow us to improve our societies in multiple ways and to take wiser decisions. The continuous progress of science and research was summarized succinctly and humbly by Sir Isaac Newton in a letter to Robert Hooke in 1675. He wrote, "If I have seen further, it is by standing on the shoulders of giants." Today we will listen to prize lectures by giants on whose shoulders present and future humans can stand, and new giants in research will surely arise. I now invite my colleague in the Academy of Sciences, Professor Tors Hans Hansson, who is the chairperson of the Nobel Committee for Physics, to introduce the laureates in physics. Once again, very welcome everybody to this year's Nobel Lectures.
This year's Nobel Prize in Physics is divided into 2 parts, with both sharing the overall theme of groundbreaking contributions to our understanding of complex systems. In nature, as well as in society, complexity is not the exception, it's the rule. Physics is traditionally associated with simple systems, such as single atoms, ideal gases, light rays, or perfect crystals. Because these systems were the first to yield to a precise mathematical treatment, while still providing idealized descriptions of real systems of immense conceptual and technological importance. However, to go further in our striving to understand, predict, and control natural phenomena, we are forced to confront complexity that cannot be understood by making small modifications of simple systems. This year's prize is awarded for fundamental work on two important problems where only a direct assault on the complex can lead to progress. To master the complexities of the coupled systems of earth, sea, ice, clouds, vegetation, and air, which determines the Earth's climate, is arguably the most important practical problem now facing science and humanity. The basic science of the complex, understanding glassy materials, is a deep problem that sends tendrils into diverse branches of human knowledge beyond the realm of physics, such as computer science and neurobiology. The first part of the prize is awarded jointly to Dr. Syukuro Manabe of Princeton University and Professor Klaus Hasselmann of the Max Planck Institute for Meteorology in Hamburg. And the Academy's citation reads, "For the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming." The first of today's lectures on the physics of climate will be given by Dr. Manabe, who was born in 1931 and educated at the University of Tokyo. Most of his later career has been in the United States, with appointments at the US Weather Bureau and later at Princeton University, where he is now active. Dr. Manabe and collaborators have developed advanced models for the greenhouse effect, as well as the general circulation models that are essential for weather predictions. And now I invite you all to listen to the first of this year's Nobel lecture given by Dr. Manabe.
It is a great honor to be chosen by the Royal Swedish Academy of Science to receive the Nobel Prize established through the generosity and foresight of Mr. Nobel. It is likewise a great pleasure to give a talk on global warming, the subject that I have enjoyed exploring throughout my career. On this occasion, I would like to thank the late Joseph Smagorinsky, the inaugural director of Geophysical Fluid Dynamics Laboratory of National Oceanic and Atmospheric Administration of USA. It has been a great privilege and pleasure to work at the laboratory unraveling the secret of climate change. Today, I would like to discuss the role of greenhouse gas in climate change using a relatively simple climate model that we constructed prior to 1990. I begin with the explanation of so-called greenhouse effect of the atmosphere. The energy balance of our planet is maintained between a net incoming solar shortwave radiation and outgoing radiation at the top of the atmosphere. According to satellite observation, the globally average value of outgoing radiation is 240 watt per square meters. Assuming that Earth's atmosphere system radiate as a black body according to Stefan Boltzmann's law of black body radiation, one can estimate the effective emission temperature of the planet. Temperature thus obtained is minus 18.7 degrees centigrade, which is colder than 14.7 degrees centigrade, which is the global mean temperature of Earth's surface. This implies that Earth's surface is warmer than it would be in the absence of the atmosphere by as much as 33 degrees centigrade. In other words, atmosphere has a so-called greenhouse effect that increases the temperature of Earth's surface by as much as 33 degrees centigrade. It is the satellite observation of outgoing radiation that has provided the most convincing evidence for the existence of the greenhouse effect of the atmosphere. In order to illustrate schematically the thermal structure and greenhouse effect of the atmosphere, this slide was constructed. In this figure, the slanted line indicates schematically the vertical temperature profile of the troposphere, where temperature decreases almost linearly with height. The vertical line segment above the slanted line illustrates schematically the almost isothermal lower stratosphere. The dot in the middle troposphere indicates effective emission center of the outgoing radiation from the top of the atmosphere. Its temperature is minus 18.7 degrees centigrade, which may be compared with plus 14.7 degrees centigrade, which is the global mean temperature of Earth's surface. The latter is warmer than the former by about 33 degrees centigrade, indicating the magnitude of greenhouse effect of the atmosphere. Radiative transfer from the Earth's surface and in the atmosphere obeys Kirchhoff's law. It's required that for a given wavelength, the absorptivity of substance is equal to its emissivity, which is defined as a ratio of the actual emission to the theoretical emission from black body. Because Earth's surface behaves almost as a black body, it has an absorptivity that is close to 1. Absorbing almost completely the downward flux of long-wave radiation and short-wave radiation that reaches the Earth's surface. In keeping with Kirchhoff's law, Earth's surface emits an upward flux of long-wave radiation almost as a black body. As this upward flux penetrates into the atmosphere, it is depleted due to the absorption by greenhouse gases such as water vapor, carbon dioxide, nitrous oxide, and methane. But it is also accreted because of emission from these gases. In short, upward flux decrease or increase with height depending upon whether depletion is larger than accretion or vice versa. Although these greenhouse gases are minor constituents of the atmosphere, they as a whole absorb major fraction of upward flux of black body radiation emitted by the Earth's surface. On the other hand, atmosphere also emits upward flux of long-wave radiation. Since Kirchhoff's law requires the absorptivity of the atmosphere to be equal to its emissivity, the absorptivity of upward flux emitted by the relatively warm Earth's surface is substantially larger than emission of upward flux by the relatively cold atmosphere. Thus, atmosphere traps substantial fraction of upward flux of long-wave radiation emitted by the Earth's surface before it reaches the top of the atmosphere, thereby keeping Earth's surface warm and habitable. So far, I have explained why the atmosphere has a so-called greenhouse effect that traps the substantial fraction of the downward flux of long-wave radiation emitted by the Earth's surface. Here, I shall explain why temperature increase not only at the Earth's surface, but also in the troposphere as concentration of greenhouse gas increase the atmosphere. If a greenhouse gas, such as carbon dioxide, increase the atmosphere, the infrared opacity of air increases, making it harder for the radiation emitted from the lower layer of the atmosphere to reach the top of the atmosphere. Consequently, average height of layer from which the outgoing radiation originates increases as the concentration of greenhouse gas increases in the atmosphere. In short, the more opaque the atmosphere is, the higher is the effective center of upward flux that reaches the top of the atmosphere. Since the effective center A of the outgoing radiation is located in the troposphere, where temperature decreases with increasing height, the temperature of the center decreases as it moves upward, thereby reducing outgoing radiation from the top of the atmosphere. The change in the concentration of greenhouse gas affects not only the outgoing long-wave radiation from the top of the atmosphere, but also downward flux that reach the Earth's surface. If the concentration of greenhouse gas increases in the atmosphere, the infrared opacity of air increases, making it harder for the radiation from the higher layer of the atmosphere to reach the Earth's surface. Consequently, there is downward shift of effective center of downward flux as the concentration of greenhouse gas increase in the atmosphere. In short, the more opaque the atmosphere is, the lower is the emission center of the downward flux that reaches Earth's surface. Because temperature increase with decreasing height in the troposphere, the temperature at the center also increases as it moves downward, thereby increasing downward flux that reaches Earth's surface. The radiative response of surface troposphere system to an increase in greenhouse gas can be regarded as a result of two related processes. The first process involves increase in downward flux of radiation that increase the temperature of Earth's surface. Over a sufficiently long period of time, the Earth's surface returns to overlying troposphere practically all the radiative energy it receives. with thermal energy being transported upward through moist and dry convection, long-wave radiation, and large-scale circulation in the atmosphere. Thus, temperature increases not only at the Earth's surface, but also in the overlying troposphere. The second process involves the upward flux of long-wave radiation at the top of the atmosphere in response to an increase in atmospheric concentration of greenhouse gas. If the amount of greenhouse gas were to increase without allowing temperature of the surface troposphere system to change, the upward flux of long-wave radiation at the top of the atmosphere would decrease, as explained earlier. To maintain the radiative heat balance of the planet as a whole, the surface troposphere system warms just enough for the effect of these processes to balance, such that top of the atmosphere flux of outgoing radiation remain unchanged despite the warming. The global scale increase of overall temperature of surface troposphere system is often called global warming. An important factor that affects the magnitude of global warming is a positive feedback process that involves water vapor, which absorbs and emits strongly over much of the spectral range of terrestrial long-wave radiation, and is mainly responsible for the powerful greenhouse effect of the atmosphere. As we know, the absolute humidity of air usually increases with increasing temperature, thereby increasing greenhouse effect of the atmosphere. The positive feedback effect between temperature and greenhouse effect of atmosphere is called water vapor feedback. It magnifies global warming that is induced by long-lived greenhouse gases such as carbon dioxide. It was the middle of 1960 when we developed one-dimensional vertical column of atmosphere in which heat balance in the atmosphere and Earth's surface are maintained through close interaction between radiative and convective heat transfer. The model turned out to be very useful for evaluating how temperature changes at the Earth's surface and in the atmosphere in response to the change in atmospheric concentration of carbon dioxide. Using the model, we obtained vertical temperature profile of atmosphere in radiative convective equilibrium, not only for the normal concentration of the atmosphere, that is 300 parts per million by volume, but also for two other concentrations, that is 150 parts per million and 600 parts per million. This figure shows vertical temperature profile of the coupled atmosphere Earth surface system in radiative convective equilibrium, which are obtained for these three concentrations. As explained already, temperature increase not only at the Earth's surface, but also in the troposphere, as the atmospheric concentration of carbon dioxide doubles from 150 to 300 parts per million and 300 to 600 parts per million, whereas it decreases in the stratosphere. In the troposphere, as the temperature increases from blue line to black line to red line, you can see But if you look at higher up in the stratosphere, temperature actually decreases from blue line to black line and red line. The magnitude of the warming in the troposphere is 2.3 degrees centigrade in both cases and is practically identical to each other. To evaluate quantitatively the influence of water vapor feedback upon the simulated warming, we conducted another set of runs in which water vapor feedback was disabled. In these runs, the distribution of absolute humidity was prescribed to remain unchanged, rather than being adjusted to maintain the constant relative humidity. From the difference among the three states of radiative convective equilibrium thus obtained, we estimated magnitude of the equilibrium response of surface temperature in the absence of water vapor feedback. We found the surface temperature increased by approximately 1.3 degrees centigrade in response to the doubling of atmospheric carbon dioxide. It is much smaller than 2.3 degrees centigrade that we got in the presence of water vapor feedback. These experiments indicate that water vapor has a powerful feedback effect that magnifies surface temperature change by a substantial factor. The one-dimensional radiative convective model was developed as an important step towards the development of three-dimensional general circulation model of the atmosphere, which in turn evolved into a coupled atmosphere-ocean model. As shown in this box diagram, the coupled model consists of three major components, which are the general circulation model of the atmosphere, indicated by green box, that of the ocean, indicated by blue boxes, and the simple heat and water balance model of the continental surface, indicated by brown boxes. Although initial version of coupled model was constructed in the late 1960s, it took 2 more decades before the coupled model with realistic geography became ready for the global warming experiment conducted in the 1980s. The result from the experiment was published in the 1980s and was discussed extensively in the first report of the Intergovernmental Panel on Climate Change published in 1990. For further detail of this study, see our book entitled Beyond Global Warming, recently published by Princeton University Press. Global warming involves change not only in temperature, but also in the rate of evaporation and that of precipitation. If a greenhouse gas such as water vapor and carbon dioxide increase in the atmosphere, the downward flux of long-wave radiation increases at the Earth's surface, as explained already, thereby increasing temperature of Earth's surface. Since the saturation vapor pressure at the Earth's surface increases with increasing temperature, it is expected that rate of evaporation from the Earth's surface also increases, so long as relative humidity of the overlying atmosphere does not change systematically. Given sufficient time, global scale increase in the rate of evaporation results in the corresponding increase in the rate of precipitation, thereby increasing the strength of global water cycle. Global warming involves not only the global mean rate of precipitation and evaporation, but also their geographical distribution, due mainly to the increase in the rate of horizontal transport of water vapor by large-scale circulation in the atmosphere. When temperature increases in the atmosphere, in response to the increase in the concentration of long-lived greenhouse gas, such as carbon dioxide, it is expected that the absolute humidity of air increases, keeping relative humidity air more or less unchanged through precipitation. Thus, it is expected that horizontal transport of water vapor by large-scale circulation also increases in the atmosphere. This is the main reason why the distribution of precipitation changes differently from that of evaporation as global warming proceeds, affecting substantially the distribution of water availability, such as rate of river discharge and amount of soil moisture at the continental surface. For example, precipitation usually increases in many water-rich regions in high northern latitude and heavily precipitating regions of the tropics, increasing river discharge and frequency of floods. In contrast, soil moisture usually decreases in many relatively arid regions in the subtropics and other water-poor regions that are relatively dry, increasing the frequency of drought. The implied amplification of existing difference in water availability between water-poor and water-rich regions present a very serious challenge to water resources manager of the world. Thank you very much for listening.